Chapter 2: Internal Energy, Work, Heat, and Enthalpy. Section 2.1: Internal Energy. How would you calculate the potential energy and kinetic energy of your cell phone? There are simple equations. For potential energy, well, you can say it's gravitational force multiplied by the height. For kinetic energy, you can say it's 1/2 mv squared. But if you take your cell phone and board an airplane, how would the potential energy and the kinetic energy of your cell phone change? And don't forget, you and your cell phone are rotating about the center of Earth. You and your cell phone are also rotating about the sun at 30,000 meters per second. So relative to the sun, the kinetic energy of your cell phone is about 90 million joules. The gravitational potential energy of your phone relative to the sun is twice its kinetic energy. It's 180 million joules. But don't forget this: the entire solar system is moving at 200,000 meters per second. And then how would you calculate the kinetic energy of your cell phone now? How would you calculate its potential energy? In the gravitational field of the Earth, the Sun, the Moon, the many other astronomical objects. Well, kinetic energy and potential energy are both relative quantities. In thermodynamics, we do not take the kinetic energy or potential energy of the system relative to the external groundings into account. They are just set to zero. Again, the kinetic energy and the potential energy of a system relative to its external surroundings are simply set to zero. Even if your phone is rotating about the sun, we do not care about that kinetic energy. And only the internal energy of the system is of interest. U denotes internal energy. Another example: if you have a gas canister of HCl molecules, the internal energy of the gas remains constant. Even if you put this canister in a rocket and the rocket is flying at 1,000 meters per second and 100 kilometers above the ground, it just makes no difference. The internal energy of this HCl gas remains unchanged. In thermodynamics, the internal energy of a system includes the attraction and repulsion between the charged particles inside the system. The internal energy also includes the kinetic energy of these particles within the system. And you may ask, what if I have only neutral molecules and neutral atoms? Well, any atom or molecule consists of nuclei and electrons. So in the end, we have charged particles in this thermodynamic system. If we look at potential energy, it can be attraction, it can be repulsion. Attraction is due to the electrostatic interaction between opposite charges. Repulsion is the electrostatic interaction between like charges. What about kinetic energy? Again, we only worry about the motion of those particles inside the system. The first law of thermodynamics tells us the internal energy of an isolated system remains constant because energy cannot be created or destroyed. In this case, we write delta U is 0 for an isolated system because U is equal to PE plus KE. Therefore, the change of the sum of PE and KE is always 0 for an isolated system. any increase of PE is accompanied by a decrease of KE, and vice versa in an isolated system. For example, if there's a reaction taking place in an isolated system, such as H2 plus F2, you get 2HF. This is a exothermic reaction. Heat is released from the reaction, but however, the change of the kinetic energy and the change of the potential energy cancel each other in this isolated system. Again, energy cannot be created or destroyed. The universe is an isolated system. Therefore, the internal energy of the universe is a constant. It's possible to have transformation from PE to KE or from KE to PE, but overall, the internal energy of the universe never changes. A thermodynamic system can be open, closed, or isolated. Let me give you 3 examples. Water puddle. Well, it's an open system because there can be matter exchange and energy transfer between this water puddle and its surroundings. What about a capped bottle? Well, it's a closed system. There's no matter exchange between the water inside the bottle and its surroundings. What about energy transfer? It is possible if the water temperature is different from the temperature of its surroundings. Isolated systems cannot have any matter exchange or energy transfer. One example is the universe. We consider the universe an isolated system. Therefore, delta U for the universe is 0. The internal energy of an open system may change due to matter exchange. Here's an example. If you add 1 milliliter water into another system that consists of 1 milliliter of water, then the internal energy of the system is doubled, going from 1 mil to 2 mils. An open system can also undergo energy exchange via heat or work. So can a closed system. When work is done on a closed system, its internal energy increases. If work is done by a closed system to its surroundings, the internal energy of the system decreases. When heat flows into a system, its internal energy increases. When heat flows out of a system, its internal energy decreases. So for a closed system, we have an equation over here. Delta U is equal to Q plus W. That means the change of the internal energy is due to either heat or work or both. Again, heat denotes the amount of heat that flows into the system. But what if heat flows out of the system? We still use Q, but Q is now negative. Work is the amount of work done on the system. What if work is done by the system to its surroundings? Then W is negative. Sometimes we write delta U subsystem for the internal energy change of the system, but it's not very convenient. So we simplify this notation to delta U without any subscript. If there's no subscript, usually we say this is about the system. It's just convention. The system subscripts for Q and W can also be omitted for the system, as well as many other thermodynamic functions. Finally, I want to say this: if you have a closed system, its internal energy can also remain constant. If by coincidence Q is equal to negative W, we plug in Q is equal to negative W here, delta U is just 0, only because Q and W cancel.